Okay, so let's get it on the screen. Algebra number 27. So we have the group SL2Z, which is all 2 by 2 matrices where A, B, C, and D are integers. And the determinant AD minus BC equals 1. And sitting in that group, we have a subgroup H, which is all matrices 1, n, 0, 1, where n is any integer. So step 1, prove H is a subgroup of SL2Z. So notice that if you take the matrix, let's say A equal to 1, n, 0, 1, then the determinant of A is 1 times 1 minus n times 0, which is 1. So A is in SL2Z. This is a matrix of determinant 1. So H is certainly a subset of SL2Z. And the identity 1, 0, 0, 1 is in H, because this is just the case n equals 0. So H contains the identity. And if you multiply two matrices in H, if you multiply two matrices of this form, just by matrix multiplication, you get this matrix, which is in H. So H is closed under matrix multiplication. And if you take A to be this matrix 1 and 0, 1, then A inverse is the matrix 1 minus 1, 0, 1. And A inverse is, you add these two numbers, 1 n minus n, 0, 1, which is 1, 0, 0, 1. That's I. So this is, in fact, the inverse. So these three things, 1, 2, and 3, prove that H is a subgroup. Okay.
Okay.
Is that okay, or is there a question about any part of that?
No, it's okay. We got it.
So there's a natural function f from H to Z, namely, so define this function by f of the matrix 1n, 0, 1 is just equal to the integer n. So this is a function from H to Z. And if you take two matrices, let me just call them X and Y. 1m, 0, 1 is X, and 1n, 0, 1 is Y. And X times Y, when you multiply the two matrices, this is what you get. So f of xy, that's this number, m plus n. But m is equal to f of x, and n is equal to f of y. So f is a homomorphism from the, let me just write over here, from the multiplicative group H to the additive group Z. And to show it's an isomorphism, we have to show it's 1-to-1 and onto. So for every integer n in Z, f of the matrix 1n, 0, 1 equals n. So f is onto. And so that's the first step. And if f of some matrix 1n, 0, 1 equals the identity, equals 0, that's true if and only if n is 0, because f of this matrix is n. So if and only if this matrix 1n, 0, 1 is really just the identity. So f is 1-to-1. A homomorphism is 1-to-1 if the kernel is just the identity. So therefore, f is an isomorphism. Let's see. Any question about that?
No.
So that's the proof.
Thank you.
Other questions? Algebra or maple?
Okay. Can you go over 19? Algebra.
So we have f from G to G prime, a homomorphism of groups. Let H be a subgroup of G. We want to prove that f of H is a subgroup of G prime. So the definition of f of H, this is the set of all elements of the form f of x, where x is an H. So if you'd like to see a picture, here's the group G, here's the group G prime. This is the identity in G, which is contained in this subgroup H. And f of H is the set of all elements where if you take any x in H, then f of x ends up over in here. So we want to prove this set f of H is a subgroup of G prime. So first of all, E is in H. E is the identity in the group G, and every subgroup contains the identity. And so E prime, which is f of E, is in f of H, because we proved that if you have a homomorphism, the image of the identity in G is always the identity in G prime. So f of H contains E prime. Second, if y1 and y2 are elements of f of H, what does that mean? Then there exist elements x1 and x2 in H such that f of x1 equals y1 and f of x2 equals y2. So y1 times y2, that's f of x1 times f of x2, but f's a homomorphism. So that's f of x1 times x2. And that's in f of H. because x1 times x2 is an H. H is a subgroup, so if it contains two elements, it contains their product. So f of H is closed under multiplication. And finally, we have to prove that f of H contains the inverse of each of its elements. So let y be an f of H. There exists x in H such that f of x equals y. That's the definition of the image. But if x is in H, that implies x inverse is in H, because H is a subgroup. It contains the inverse of each of its elements. So this means that f of x inverse is in H, is in f of H, and f of x inverse, we proved, is the inverse of f of x, and f of x was y, is y inverse, is in f of H. So f of H also contains the inverse of each of its elements, and these three steps together prove that f of H is a subgroup of G prime. So there are three steps to the proof, and they're all important to do correctly. Okay. Any questions about this? Should I do part B, or should we go on to something else?
Yes, please finish part B.
So again, we have groups G and G prime and a homomorphism F from G to G prime. And now we're looking at this going in the opposite direction. Here's G prime, here's F. We take a subgroup over in G prime, and we let F inverse of that subgroup H prime be the set of all x in G, such that f of x ends up in H prime. So we're looking at this F inverse of H. This is every x that gets mapped into H prime. And we want to prove this is a subgroup. But we know, first of all, that f of the identity in G is the identity in G prime, which has to be in H prime because every subgroup contains the identity. So if E gets mapped to E prime in H prime, then E is an F inverse of H prime. So this inverse image certainly contains the identity. Second, we have to show that F inverse of H prime is closed under multiplication, so that x1 and x2 be in F inverse of H prime. So that means that f of x1 is something in H prime. Let me call that y1. And what I can call y2 is f of x2. That's another element in H prime, And H prime is a subgroup. So therefore, y1, y2 is in H prime. And if we compute f of x1 times x2, because f's a homomorphism, This is f of x1 times f of x2, which is y1 times y2, which is in H prime. So x1 times x2 is an f inverse of H prime. Right, so, I mean, this is just a chain of reasoning that you have to think through very carefully. So you have a subgroup H prime and G prime, and we look at this set, which is called the inverse image, and we want to prove this is closed under multiplication. So you take any two elements, x1 and x2 in this set. That means that f of x1 is an H prime and f of x2 is an H prime. So I can call those elements y1 and y2. But H prime is a subgroup. It's closed under multiplication. So if H prime contains both y1 and y2, it also contains the product. And if you look at f of x1 times x2, because f's a homomorphism, that's f of x1 times f of x2, that's y1 times y2, which is an H prime. So x1, x2 is in the inverse image. So that proves the inverse image is closed under multiplication. And suppose x is in f inverse of h. That means f of x is some element y in H prime, and H prime is a subgroup. So y inverse is in H prime. And what is y inverse? Y inverse is f of x inverse, which we proved is f of x inverse. So f applied to x inverse is in H prime, which means x inverse is in f inverse of H prime. Again, every one of these equals or whatever requires some proof or some explanation. But this is in fact the complete proof that if you take any element of f inverse of h, its inverse is also in f inverse of h prime. Its inverse is also in f inverse of h prime. So 1, 2, and 3 together imply that H prime is a subgroup. That's the proof. Any questions about Maple? Anyone from Maple here? No? Okay. Any questions about anything? Is that it?
Oh, Professor.
Yeah.
Oh, sorry. I was just looking at the final exam review sheet for Maple. Could you show how to do the second question?
Which class?
156.
Okay, let's see. So this is the sheet that you're asking about?
Yes.
And you want question number 2?
Yes.
Okay. So Let me screen share to that. Oops, that's not what I want. So this is some review that I've done already. And I think I've done that problem at least once. So let me just find it. Yeah, here it is. So let me try to do something. Oops, that's not what I want to do. So can you see both sheets right now?
Yes.
Okay. So we want to plot these two lines on the same graph. So the simplest thing is to solve each of these for y in terms of x, because the plot function lets us plot a function of x. So if I take this equation 2x minus 9y equals 7, I say solve it for y, and I get this. I call it y1. And I solve the second equation for y. I call that y2. I got this. That's what you do. And then you plot y1 and y2 together, and you get this. So that's one way to do it. Now, there's a second way to do it using where you don't solve for y, but then you have to use implicit plot. So I open the plots package, and then with implicit plot, I just write down the two equations, and I give a range. This is what it is. And I get the same plots. So you can either solve for y in terms of x and plot the equations of the two straight lines, or you can use implicit plot and get the equations of the two straight lines. So both methods work nicely.
Okay, because I did this yesterday, and like I did exactly the same thing that you did, but I was just wondering if like I had to give the points for the solution, right?
What do you mean?
Where they intersect.
Oh, okay. So that's the second part of the problem, to find the solutions of the system of equations. So so I could just do it like this. I could say solve these two equations and I'm solving, oops, for two variables. So I put the variables also oops. X comma y. That's the solution. And if I wanted in decimals, I would use fsolve.
All right. Okay. Thank you. Because I did that, but I did it like if you were to write it down, but I got the same answer.
Right. But Maple will solve equations for you and you don't have to do any work.
Mm-hmm. Thank you.
Sure. Any other questions?
Can you do algebra 2 and 3?
Sure. Just a moment. Okay, so let's get back to algebra. Oops. Which number? Which number on the algebra?
Two and 3.
2 and 3. Okay, so problem 2, want to prove that if R divides ST and the greatest common divisor of R and S is 1, then R divides T. This line is just shorthand for divides right now. So let's see. So if the greatest common divisor of R and S is 1, that means that there exist integers, X and Y, such that Rx plus Sy is equal to 1. And R divides ST means ST is equal to R times Z for some integer Z. So take this equation and multiply by T. You get RTX plus STY equals T. But ST you can write as RZ. So RTX plus ST is RZY equals T. And from this, I can factor out an R. This is R times TX plus ZY. So R is an integer, and this is an integer, and this product is equal to T. So R divides T. Questions about this? And problem 3, if A1 is congruent to A2 mod M, that means that A1 is A2 plus some multiple of M. And if B1 is congruent to B2 mod M, then B1 is B2 plus some other multiple of M. So if you add these two equations, A1, or if you subtract those equations, right? I mean, here are the equations. A1 equals A2 plus MX. B1 equals B2 plus MY. If you subtract, you get A1 minus B1 is this minus this. A2 minus B2 plus MX minus Y. So this number is equal to this number plus a multiple of M. So A1 minus B1 is congruent to A2 minus B2 mod M. That's the proof. Any questions about that?
No.
Professor,
Yeah.
for Maple, for question 4 for the final review, could you show how to do that? Because
Which
I'm having
Maple? Which class?
156.
Okay, which problem in 156?
Question 4.
Okay. So let me go back to the Maple worksheet. So math 156, problem 4. We have a function f. X goes to, oops, this has to be a colon. F goes to the tangent of 1 plus exp of minus x. Okay. So let's I can do it step by step. First of all, the first derivative is the derivative of f. That's it. The second derivative is that. And the third
Okay.
derivative.
I tried to loop.
Sorry, what?
I tried to take the derivative. I thought we were supposed to use like a do loop. A do
Okay,
loop.
then this is what you would say. For n from 1 to 3 do, put in my n do, and it would be what we want to compute is d at n of f of x. And we get these three functions.
Okay. Thank you.
Yep.
Oh, and Professor,
Yeah.
the question after that. So question 5, it says compute the first 12 derivatives of the function.
Right. That you definitely need to use a loop.
So like the loop is working, but my computer just like, I don't know, it just started to freeze after it got past what, 6? So
Well, let's see what my computer does. So here, this is problem 5. So
yeah.
the function is different. It's g. X goes to 8 times x to the 5th minus 31 times x to the 4th plus 3 times x cubed divided by 24 times x to the 5th plus 7 times x squared minus 111. So that looks like it's the right function. And it's going to be the same loop, except that the function is not f, it's g, and you're not going to 3, you're going up to 12. So this should be some big mess, but let's see what happens. Yep, I got it all.
Okay. Thank you.
Yeah, it's a lot of printout. But it works.
Yeah, I'm just trying to scroll back up past all of this as my computer's already.
Professor. Hello, Professor.
Yeah,
Could you do number 10 from algebra?
okay. So problem 10 on the algebra review is the following. So I is a non-empty set of integers closed under subtraction. So I is not the empty set. So there exists some element x and I. And I closed under subtraction means x minus x, which is 0, is in I. So I contains 0. So the first case is I only contains 0, nothing else. And in that case, I is the set of all multiples of D, of 0. Because anything multiplied by 0 is 0. So I is 0z. You just take D equals 0. So if I only contains 0, then you can choose D equals 0, and that's unique. And in the second case, I is not just 0. So there exists x in I different from 0. If x is positive, stop. That's nice. If x is negative, then because I is closed under subtraction, 0 minus x, which is minus x, is in I, and minus x is positive. So in every case, I contains some positive integer. So this is the first part of the proof, and I have to ask if you have any questions about this.
Professor, can you please move the paper up a little bit? Thank you.
Right. So by the minimum principle, which says every non-empty set of positive integers contains the smallest integer, I contains a smallest positive integer D. So we're letting D be the smallest positive integer in I. And then we prove that this D is exactly what works. I is going to be equal to DZ. And the way you prove that is, first of all, you notice that if X is in I, then we prove minus X is in I. And because I is closed under subtraction, X minus minus X, which is 2X is in I. And then 2X minus minus X, which is 3X is in I. And as you continue, you see that NX is in I for all N. And so minus NX is in I for all N greater than or equal to 1. So minus NX is in I for all N greater than 1. So I contains all multiples of any element in it. So let X be, or I don't know, that A be any element in I. Divide A by D. You get A is DQ plus R, where R is the remainder between 0 and D minus 1. So we have DQ is in I, because D is in I, and I is closed under subtraction. So A minus DQ, which is in R, is in I. And R is between 0 and D minus 1, but D is the smallest positive integer in I. So R is smaller than D, it can't be positive. So R is 0, and A is equal to DQ, which means every element in I is a multiple of D. And that's basically the proof.
Is this question will be in the exam?
I don't know, haven't made up the exam yet. But the exam covers the entire course. Everything, whether it's on the review sheet or not. But certainly if it's on the review sheet, that can be included on the exam. Okay. Let's see, I have to leave because I have another group of students that I'm meeting at 5 o'clock. So are there any last questions before we go?
Is this the last review session, Professor?
Sorry?
Is this the last review session?
No, I can hold another one. I can hold one tomorrow.
Okay, yes, please.
Yes, Professor.
Yeah.
So I'll send out probably probably at this time
Okay.
at 4 o'clock. Let me just check that I don't have any other exams then to give. Yeah. So let's say tomorrow at 4 o'clock, but I'll send everyone an email announcement about that tonight.
Thank you very much, Professor.
Okay.
Yes, sir.
Okay. Be well, everyone. Bye.
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 Oh, Professor.